Okay, let's get going with Chapter 6, Chemistry in Context, from the 9th edition. So Chapter 6, we're going to look at energy and alternative sources. How much energy is used in the world? And you start to get an idea of that when we look at Chapter 5. What is solar energy? And we'll look a little bit more at that as well. What is radioactivity? We'll spend a fair amount of time talking about radioactivity. That is one of the key topics or subjects of Chapter 6 and our discussion. This will be only one lecture, by the way. How do nuclear power plants produce electricity? You'll get a chance to return to that. You've looked at it already in Chapter 5. One method of using fossil fuels. We'll look at it again in this chapter. What's the environmental impact related to fossil fuel power plants? And that's pretty important. And what are the types of renewable energy sources? So that's what we'll look at in this particular chapter. All right? Here we go. By the way, this chapter is a lot of verbiage, a lot of things to read in this chapter, and I will read through almost all of it. Okay, so be prepared for that, and we'll talk about it as well. Nuclear fission is the splitting of large nucleus into smaller ones with the release of energy. That is a key definition that you'll want to know, and that is the basis for what's going to happen in terms of understanding nuclear reaction and nuclear chemistry and how it's used. It's splitting of larger nuclei into smaller ones with release of energy. And it's that release of energy that's important to thinking about nuclear chemistry and nuclear energy. So that is a definition you want to make sure that you know and hold on to. Energy is released because the sum of the mass of these fragments is less than the original mass. So the sum of the mass of the fragments is less than the original mass. You get it? So you have a mass that splits into fragments, and then you have this portion that we're going to look at, this missing mass. Okay, it's about 0.1%, and it's been converted into energy according to Einstein's equation. Energy equals mass time speed of light squared, and that's what makes it so impactful. So you take this very small mass times the speed of light, which is an exponential. So it's right, makes it really a lot of energy release, and that's why nuclear fission works with a small amount of material, yet a lot of energy. Einstein's equation is what explains it. So essentially, that mass, if you will, is traveling at the square of the speed of light. All right. Now, you note that the speed of light is 10 to the 16, 9 to 10 to the 16. So when you look at that, that's a lot of energy, right? So you can run all the numbers and you can calculate it. And nuclear physicists and others who work in this field do this all the time. So whether it's for power or a weapon, it's a lot of energy. Okay, we will be talking about where it's used for power and not as a weapon. But the energy is the same. You see, the energy is the energy regardless of what you use it for. All right? Well, actually, I said we will actually talk about where it was used as a weapon as well. So I'll take that back. We will talk about both of these in Chapter 6. Okay? And it's used for both reasons for energy. You need the energy. Now, when we talk about nuclear reactions, we have to think about isotopes. And we think of them and we call them radioactive isotopes. For instance, U-238 is written as such. The mass number, this is the mass number. So it's the number of protons plus the neutrons is what we have here. And then we have the atomic number. So the atomic number, that's what we see on the periodic table, all right, for each element. And each element has a characteristic atomic number, therefore has a characteristic number of protons, which uniquely identifies it as that specific element. So nuclear fission is initiated by neutrons. In other words, a neutron essentially impacts or collides with this particular isotope of uranium, And when it does it, it basically excites the molecule. So now it's radioactively impacted uranium. And note here what happens. It now has one more neutron, right? You get it? Because protons stay the same. One more, the mass number increase. And the reason mass number increased because it has one more neutron. Okay, you recall that from being able to determine mass numbers, right? But when this excited state, it doesn't like to stay like this. So basically, it releases this in the form of an isotope, barium 141, okay, krypton 92, and 3 more neutrons. And what's going to happen to these 3 more neutrons? They're going to keep doing the same thing. And so in the next slide, you're going to see this is what starts this chain reaction. So we get this neutron and then from some source, okay? And so once we impact the uranium, we get this isotope, and then this splits into these other materials, which are stable, actually. Each of them having their own unique mass number. And we get the 3 neutrons. And this is why the reaction keeps going in a chain, because you keep generating these neutrons. So 3 neutrons are generated. All right? Now, you will have to know how to do the math on this. It's finger and toes math. It's pretty straightforward. You just make sure everything adds up. Is that straightforward? Okay? The science is a little bit more complicated. The math is pretty straightforward. So the superscripts, notice here we have 1 plus 35, so we get that. Okay? Here we go. So we have the left side. Then we have these must all add up across the top to 236. Does everyone see that? So here, after it's impacted, after it's excited, after it's actually, we say excited, it's basically destabilized, okay, is really what happens here. So it's destabilized. And now, which is excited, we get all these different atomic mass numbers that must add up, plus the contribution from the neutrons. And the subscript here we have 92. This must also add up. So there must be a balance of the mass numbers and the atomic numbers on both sides of the equation. Remember, conservation of energy, which is conservation of mass. You can't destroy energy nor mass. Okay, but you can transform it into another form, and that's what's happening here when we do nuclear reactions. We're taking this form of energy and we're transforming it into another form, and we get these species, these highly reactive or highly energetic species, okay, and it attacks some others, and we'll show you that hopefully at the next slide. This is what creates a chain reaction. So they're going to call these 3 neutrons, right? We got these 3. Let's follow it through here, then we'll read it. Take a look here. We have this neutron that's generated from some source. This is the original generation. There are ways to do that, generate in a lab or generate it somewhere. You get this neutron. So you hit it with this, hit the uranium-325 with this neutron. That neutron splits off into a stable krypton, barium here. And now we have these 3, right, neutrons left over that reattack uranium. This one also does it too, just Crowder here to show it on this diagram. I assume that's why he didn't do it. Or it spins off and it floats around. Eventually it finds a place to attack, okay? So, or impact or, collide with. So each of these collisions creates a new stable species, which this author shows off the sides here, and 3 neutrons, which now impact or collide with another uranium, and this goes on and 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 on.
So it just doesn't stop that.
There you go. It just goes. It eventually reaches a point to where it's non-harmful. Okay? To most organic matter.
It's because of the dispersion of how it's like less.
it works in half-lives, and we're going to show you that too. Yeah, it's asymptotic. Okay, it's the classical stuff in calculus that you hated, called the asymptote. Okay, all right. It has this range, right, and limit. Okay, all right. So here, that's what's happening here. So this is why this energy is so powerful, and also why it's so useful. And the real question is, how do we be responsible with it? That's the challenge in terms of radioactive energy. How do we be responsible? So let's take a look here and read through this. For fission of U-235, this is the mass number based on this isotope shown on the slide. One neutron produces various fission products and 3 additional neutrons. That's what we're showing you here. Each of these generated neutrons can initiate the fission of another U-235, which is what we've shown you, which would generate even more, and so on. And that's what we mean by on and on and on. This is known as a chain reaction. So you want to know what a chain reaction is, in which one of the products becomes a reactant, making it possible for the reaction to become self-sustaining. That's what happens. So chain reactions are self-sustaining. Okay, right? By analogy, in polymer chemistry, chain reactions are used to make the plastics, but we quench them at some point. We stop them from continuing to go on and on. Okay, and some of them are self-terminating. So here we have these chain reactions, and they go on. Once you start it, it goes on, and in this case, excuse me, it goes on until it reaches some concentration that's non-harmful, non-lethal. The critical mass. Now this is important, and this is why accumulation of radioactive materials is so important around the world. When you hear these discussions on the news and in political, they're talking about they're accumulating radioactive material. This is why. The critical mass for U-235 is 15 kgs, which is needed to spontaneous fission in the presence of neutron source. So if you get 15 kgs, and it sees a neutron source, it can take off. A nuclear reaction can happen. And so that's what happens. You throw a switch that creates a neutron source, and once that neutron source is initiated, those 15 kgs just goes. Okay? All right? So accumulate. So this is why you hear these discussions about accumulation of nuclear waste and accumulation of radioactive materials, and this is why it's important, because have that amount, a neutron source can go kaboom. And when it does, this is what happens. So we have this energy and the delta mass times the speed of light. So how much energy is released? And I'm going to go to the bottom of the slide, and you see the answer already. In this particular case, we'll back up and walk through it. 22. This explosion could be equivalent of 22,000 tons. Okay. So what you have here is the mass. So for the fission of 1 kg, got it? That's just 1 kg. Right with it? 1 kilogram, 1 milk jug. Okay? All right, so about a milk jug. All right? Yeah, I think it's about right. Something like that. So the mass of the products is 0.1% less than the original. Okay? Therefore, the change, the delta is 1 time 10 to the minus 3 kgs. That's it. That's the delta. So you take that delta times, right, 10 to the 8, and we walk it through the math. You see what's happening here? Square it. And then you run the math through, and we get 9 times 10 to 13 joules. Okay? And we've already talked about joules before, right? The energy in joules each time you heartbeats, 1 joule. So this is a lot more energy, and we showed you a chart in chapter 5. This amount of energy alone, and this is 1 kg, is 22,000 tons of explosive TNT. That's a lot of force. So imagine 15 kg. Okay? All right? So the real key point here is it doesn't take very much to produce a lot of energy. That's why it was so attractive for this plug here.
Yeah.
That's why it was so attractive for nuclear power plants. Okay, because small amount, right, produces so much energy. That brings us to looking at nuclear power plants. In chapter 5, just a minute. Okay, in chapter 5, we talked about power plants, right? This particular slide is the same power plant, except that, notice here on the left side, we changed what? The burner. Okay? In a fossil fuel power plant, we have fossil fuels for the burner. Okay? Fuel oil and coal. In a nuclear power plant, we replace that burner with a nuclear reactor. Follow? So we get ours. So we have this potential energy here that when we hit it with a neutron, it's converting this kinetic energy that produces the steam for us, right? Steam pushes the turbine. The turbine turns a generator. The electrons run in a 3D structure in a 3D fashion along the wires. It goes around and around the building, passes through some point of resistance and some point of contact. Voila, let it be light. You get light bulbs glowing everywhere. And you also get energy to plug in your cell phone or your laptop. You get all these wonderful things happening because of electricity. And then it goes back, and you've had this before. It condenses. The warm water goes to a cooling tower. And if you're driven along the Cedar Point route, don't take the turnpike, can't recall what highway it is, and go to Cedar Point, you'll see these tall towers. That's what these are. These are cooling towers. Okay, so this isn't, when you see this isn't a nuclear reaction that you see the steam coming off. There's a nuclear reactor. No, that's actually the cooling towers you see. And those cooling towers go into a cooling pond. You pump it back through, pump it through again, and here. All right? So everyone follow. This is what a nuclear reactor looks like. Now, there's a couple of differences between a fossil fuel plant and a nuclear plant, and let's talk about those. In a fossil fuel plant, you do not have this huge concrete building around it. This is a containment building. Notice that it not only contains the reactor, but it also contains it's a retainer building for the steam generator as well. All right. So this building is where it houses it's called the containment structure. It's where it contains the reactor and the steam, because this is the most dangerous part of it. Okay. Let's see what we missed here. Okay. Now, one thing is very important to note and know, that the same energy coming from a fossil fuel plant, that the energy from a fossil fuel plant is the same energy that comes from a nuclear plant. The energy is not the same. It's not any different. Let me repeat that in case someone, okay? The energy is exactly the same from a fossil fuel plant and from a nuclear power plant. You get it? The energy is the same. Similar if it's a solar plant as well. The energy is the same. Your energy is not radioactive energy. Okay? Be aware of that, because there's some conspiracy theories about that float around occasionally. That is not scientifically true. Okay? So why do you use these? You use these so you can get more bang for your buck. okay, more power with less material. As it turns out, in the middle of Michigan, there is a plant in Midland, Michigan that up until about 89, I think, no, 84, somewhere there about 84, somewhere there about, that plant was going to be a nuclear power plant. And it was starting to be built as a nuclear power plant. I think the political view was at that time that Midland, because it is headquarters of Dow Chemical and people are very astute about these kinds of things, and all these scientists in town, all these very brilliant people, understand science, et cetera, they will welcome a nuclear power plant. Turned out not to be true, because some of the very people who understand the science very well also did not agree with having it there. And so that plant was turned into a fossil fuel plant, actually to coal, to wood, to fossil fuel plant. During that time, Dow Corning was going to take some of the steam, you see the steam shown here, from that to power some of it across the road, and still does take steam across the road to that plant, but it's going to take steam from that. And it planned for it, and it plumbed for it. Well, as it turns out, because things got held up, Dow Corning put in its own plant, which was a wood burning plant. It burned wood chips. So they were getting wood chips off of places where they farm trees. They grow chop trees down and cut them out. So you have, again, wood being a simple fossil fuel, etc. So my point here is that occasionally this power meets with a lot of pushback. There are those who prefer not to have it, and you perhaps can understand why, right? It doesn't take very much. Okay, the catastrophe for it tends to be not be so good, and we're going to talk about a few of those catastrophes, at least, in this lecture. Okay. Now, we talk about you have to generate the neutrons, right? You have to spark it with something. There has to be a source to kick it off, to initiate it. So to initiate it, one way to generate neutrons is to use plutonium, beryllium, and alpha particles. Any of these will impact or allow you to generate those neutrons to initiate the chain reaction. Let me show you here. Notice that this, again, it has to be a balanced equation. Balanced equation is very important. We'll be working on this on Monday. Okay, Monday is our math day. Right. One way to generate these neutrons, is shown here, again, it has to be a balanced equation. So we have the balanced equation here of each of the species. You can see them right shown here. So we have plutonium, going to uranium, going to helium. We have helium and beryllium. Again, the mass numbers add up. The number of protons add up. Okay, and here we get gamma radiation. Gamma radiation, that's the Incredible Hulk. And that's the radiation that we really would like to avoid. And it's not good for organic matter, you and I. So we have the gamma radiation, neutrons, and we have the helium alpha particles. So all of these can generate. So you generate this, so this can help push the chain reaction, Which one did I miss? Alpha, and the gammas. Yeah, I'd say gammas. And here, both of these. So we have here, here, here. That's right. Okay? Again, all of these will help push a nuclear reaction. So let's talk about that energy production. Electricity generated by nuclear and fossil fuels is identical. We said that already. And you already know from chapter 5, right, that there isn't that much that there isn't a lot of energy produced from nuclear power plants. You know that already, right? We had that. Perhaps I'll add that slide back to this section. But you know that over 72, 70, some number like that, over 70% is fossil fuel. Less than 20% or some number like that is renewable, and I think the nuclear is in the single digits. But be sure you take a look at that slide again in chapter 5. But here we have it. It's very efficient, but it's not used. And one reason is the concerns with what do we do with it. Okay, we'll talk about that more in this chapter. But let's take a look at this. So here, this is what the plant looks like. These tall towers, these are what? These are the cooling towers. These are not the nuclear reactors. So when people see the steam blowing out, they look. No, that's just condensation. That's just water. That's good. And it's white. That's good. This is good. Okay? So these are the cooling towers. This is where the water is coming up and it's cooling. Okay? These two buildings right here, these round, small silos, these are the reactor buildings right here. Okay? So the taller buildings on this slide, the taller structures on this slide, are the cooling towers, and the smaller silo-looking buildings to the right side, these are the nuclear reactors. The radio energy production is power. So the rate at which we produce energy is called power. Okay? A common unit of power is joules per second, which is, or watt. We think of it in watt in our everyday walk around life, a 20 watt or so many watts. So we think of it in watts. So now you know each time you say a watt, you're saying a joule per second. That's a rate, right? Because you have to have energy per time. So the rate at which it's produced is called a watt. So each power plant will put out a certain wattage. Single nuclear reactors have the maximum power capacity between 500 to 1,300 megawatts as compared to 600 megawatts for a typical coal power plant. So does everyone now see the difference in why the availability and the potential for nuclear power is tremendous? You can essentially double the wattage coming out of one plant if you go to nuclear power with less material. That's what's so important about nuclear, and it's really a good scientific, a good piece of technology. And again, it meets with a lot of precautions, and we're going to show you why some of those precautions are there. So, you know, those power plants are running. What do power plants run at? What do we tell you?
5%.
Yeah, about 35. We know it's less than 50, right? Run about 35% efficiency. So essentially, in one plant, at that 35% efficiency, and okay, assuming that nuclear is going to be about the same, but they're all less than 50% because of these mechanical parts. Is really as much the mechanics of it, of the plant, the mechanical operations, and simply operations. Each step is not that efficient, so those operations reduce that. So essentially, you could get, for less material on site, you could get more power coming out of that plant, which means instead of building two plants, maybe one plant would take care of that area. Does everyone follow? That's why it's talked about and thought about so much, and why many governments are really trying to put it in place. But it does meet with, again, concerns from people that live there. So just a note here that what a megawatt is, 1 times 10 to the 6 watt. You knew that. Now, you've been in my class long enough to recognize that it's not too often that I talk in detail or very much about the scientists who really did the work. Okay? It's absolutely true that it'd be rare to find a scientist with a big ego. Okay? We don't believe the press on all of the scientists having big egos. Okay? All right? The reason we don't have big egos is because we recognize and realize we are the most brilliant people in the world. So there's no reason to have an ego. Okay? So it's rare that I talk about the scientists, right? Who they are. But this is just really one remarkable piece of work that this scientist really deserves to get some attention for. So, yeah, you might guess I'd probably ask about her. Okay? Marie Curie. Who really developed or coined the word radioactive, essentially, is given credit for that, for spontaneous emission of radioaction by these elements, okay? 2 Nobel Prizes, 1 in chemistry, 1 in physics, and that is just remarkable and doesn't happen too often. It's not too often that chemists and physicists can agree with themselves in their own minds and do this kind of thing. So it's just really remarkable. So she gets a lot of credit for what's happening in terms of radioactivity. So I always include this slide because it's just simply, her work was brilliant, frankly, okay, and deserves a lot of recognition for that. So there you go. there's my one real firm historical point. Yeah, I'd like to ask about this person. So here's some things that we all learn and start to understand from this brilliant work. Radioactivity includes alpha, beta, and gamma rays. Okay? You'll want to know that. And here's what they are and what they look like and what the technology looks like and how we use them to try to harness, if you will, this energy, and how do we try to effectively use this energy, and also how do we protect the environment from this energy being mishandled or misused. So here we go. Ready? Let's take a look at this slide. We have the alpha, the beta, and the gamma. The alpha, you see there, is helium-42. Okay, it's called an alpha. And it has 2 protons and 2 neutrons, but you knew that already, right? Because you saw H42. And you know, here's the number of protons, so you subtract 4 minus 2, you get the number of neutrons. It has a +2 charge. You'll want to know that. Okay. You will want to know the charge of each of these. Beta, shown here. Electron. So it's 1 electron minus 1. Then gamma, no charge. It's a photon. So essentially, Banner on the Incredible Hulk, which will be in the Avengers next movie, Banner was hit with photons. It was hit with the energy that comes out of the Raccoons and Guardians of the Galaxy's gun, except in this case, it was energy that the Incredible Hulk absorbed, the energy. And he went to an excited state, and when he came down, he comes down to the Incredible Hulk with all this bent-up energy that he releases in vengeance upon his foes. That's essentially what gamma photons do. They're excited molecules, okay, and they wreak havoc on organic matter. Gamma So this gamma radiation, gamma rays are part of electromagnetic spectra, which you know, with more energy, shorter wavelength than X-rays. You learned that when we talked about the electromagnetic spectra, right? So we all recall that. Okay? All right. Radioactive decay. This is what happens to radioactivity or radioactive species once they're released, and essentially exist in the environment. By the way, okay. Let's start by looking. We'll just start here, looking at the graph here. What we have is these 2 ways that it decays. It decays by alpha decay or beta decay, and now you know what alpha and beta means, right? Shown here, alpha positive and beta negative. So here the red lines show alpha decay, and alpha decay goes down to a new species, okay, at its isotope. Then we get a couple of beta decays, and then we get this long string of alpha decays, and this is for uranium. This is uranium's decay, radioactive decay. Each species has its own unique one. And here we get another beta. These alphas, we get more betas, and essentially, voila, we end up down here at lead. You get it? Okay? So essentially, these one element, once it decays, become some other stable species, which is also an element. Does everyone follow? All right? So it's decaying, and there's only so many electrons, neutrons, protons, etc. They can use in this process, and eventually it stops, or it reaches some state where it prefers not to decay any further than lead. Okay? So radioactive isotopes undergo decay until they reach a stable species. Stable, in this case, uranium goes until it reaches lead. All isotopes of all elements with atomic number 84 and higher are radioactive. You get it? So where do we have 80? So right here. Get it? So now once these undergo this radioactive decay, we decay, the mode in which they decay is called its half-life. That's what I want to get to. Okay? It's its half-life. You get it? And that's how we talk about it. So it's this half-life has several half-lives. Okay? It's not quite a cat. Okay? But it has, okay? Cat has 9 lives. This has half-lives. And this half-life goes in a half-life, goes in a half-life. And that's what this curve shows here. Okay? This curve shows the half-life, and then half of the half-life. Does everyone follow? Then half of the half-life, 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 half of the half-life. You get it? On and on and on. That's why. This is why you study calculus, just so you can understand half-lives in my course. Now we just gave value to calculus, right? Yep, that's it. Okay? But this is what it is, okay? And so this continues. Okay? So half-life time required for the level, and we're going to show what these are, and it's going to show you why it's so important that we understand nuclear chemistry. A half-life is the time required for the level of the reactivity to fall to 1/2 of its initial value. You get it? To 1/2, and that's all. That's what it means. You want to memorize that definition. All right, now watch this. Each radioisotope has its own half-life. Some, like plutonium, right? Okay, goes to 230. It goes to 239. Takes 24,000 years. So what's that mean? That means it stays around a long time. A lot of generations. That's the key point that we want to make sure you at least grasp here beyond the numbers, right? It'll be here. 24,000 years, long time, right? Okay. Let's see here. Whereas, this is, oh yeah. The other isotope, so it depends on the isotope. So 239, yep, 24,000 years. But isotope 232, 8.5 minutes. Decays very quickly. You get it? So the isotopic value really matters. So your mass numbers, which determine the isotope, which determine the number of neutrons available, really matters when we choose these. And that's why it's so important to understand. And that's why, again, global governments try to govern how these materials are used. Because that's a long time for that radioactivity to stay around, right? Okay? For that material. And here you have it, this table. I expect to memorize the entire table. No, I don't. No one memorizes this table. Okay? If you need this table at any point, I'll let you look it up. Okay? But I want you to be sensitized to the magnitude of what we have to understand about radioactive technology and nuclear fission and things of that nature. Look at these half-lives. Does everyone see this? Depending on the isotopes, all the way down to here. It's a few days, so iodine, not bad. A couple of iodine, pretty, okay. Radon, which is a home pollutant, indoor pollutant. You learned that already. So, what's that? 3 days down the half-life, whatever's initial concentration down to 3 days, so it goes. Okay. And here we are, found in used fuel rods of nuclear reactors. Yes. So this is why the fuel rods, keeping the fuel rods and knowing where the fuel rods are is very important as well. So everyone follow. So this slide is really a sensitivity slide to help you understand the impact of nuclear reactions. Half-life calculation, I expect you to be exposed to have an idea how this works. There is a question. There will be a question on the exam. There will be a half-life question. If you look at this slide, you'll know how to answer it. So we take the number of half-lives, 0 to 6 in this particular case. So it takes you, here you at about the percent of decay, about 98%, when you get about 6 half-lives here. And so this is just a delta, right? I think this is intuitive, right? The percent remaining, if you know how much decayed, the rest is how much remains. So I could ask you how much remains. That means you know how much decayed. Okay? And so the math, you can do the math or you can memorize the math. For me, in 102A and in 102A, I'm less concerned about this bit of math for you as I am about you understanding the concept of what this decay, what these decays look like. Okay? All right? But this is all basic math to get here. So let's talk about what we do with the materials. The long half-life of isotopes produced for nuclear reactors means that the nuclear waste will emit radiation for thousands of generations. Not thousands of years, but thousands of generations. Okay? That's a lot of great-grandkids to come, isn't it? This is why where it's kept is so very important. Okay? Most nuclear waste is stored on site. However, countries are trying to develop long-term underground storage options, like the Yucca Mountains in Nevada. As of 2016, it appears that this repository will not be completed due to ongoing scientific concerns. At one point, this was being built, okay, where this is going to be the site where nuclear power waste could be stored. But even the best of the scientists during that time thought that the containment of it might not be possible. And then you had the issues of what if a terrorist attack on that site, okay? You drop a nuke to start a nuke, right? And would it be worth it for a country, you know, who decided to attack the U.S.? Would it be worth it to do that? War is war, and it has the rationale for war is too challenging for people like me to figure out. But as the scientists looked at it, said it is possible to lose containment. That was the bottom line. Okay. And the question is, would that containment be catastrophic? Yes. So that means now all nuclear waste is stored on site. Note that, because I asked that question. I asked that very specific question. Where is nuclear waste stored? All nuclear waste. So when the site's built, it's built to keep the nuclear waste there as well. Okay? Which is also one of the concerns with building new plants. Where that means you're going to need a lot of acreage, right? But not really a lot, because you're using small amounts, but you need acreage. And then the question is that land, that footprint near, you know, a major city, a major whatever, and you say major city, you say, you know, heck, I'm just a little farmer out in the middle of nowhere, but I still value my land. Follow? So you have all those concerns that go on. So the nuclear waste is stored on site. That's it. At one point there was some caverns somewhere, I think in the Detroit area, somewhere in Michigan. I don't recall the details on this, but they had looked at those caverns too, as well as storms. There were some salt deposit mines in places. They looked at old abandoned mines in the Virginia mountains. They looked everywhere, a lot of places. Look for anything that's underground, but today it's stored on site. The risk of nuclear power. This is a big risk. 1986, reactor number 4 at Chernobyl, nuclear power plant, 100 kilometers north of Kyiv, blew up doing a routine daily operation. Nearly 9 tons of radioactive material. 9 tons. Is everyone? I mean, I don't know how to get that. So they compared it 100 times as much as Hiroshima. And you've all somewhere in history heard about the Hiroshima, right? That's a lot. You get it? That's huge. That's devastating. And it really, winds over the following days, mostly blowing northwest, carried fallout really far as, okay, the Baltic region. Okay. The control rods were made of graphite, unlike those used in the U.S., okay, which are not graphite, and I forget what material the U.S. makes them out. I should look that up again at some point, which caught fire. The bottom line is the type of rods are very, very important to how the radioactive materials contained. But this was basically a catastrophe of neglect. Okay, yeah.
Obviously, Chernobyl is still radioactive right now, but what was the fallout for Belarus and other areas?
I'm sorry, will the fallout affect other?
Belarus and other areas, like how harmed were they?
They're not. It's for them. I mean, you can't destroy nor create matter, right? So whatever happens there, we experience in some fashion, okay, around the world. It's the nature of equilibrium, okay, in the world we live in. We're all affected. But the direct impact or the meaningful impact is less. There are those who argue that, yeah, that things may be happening, but as best can be detected, it's not. Yeah, that's a good question, though. So, let's see. So what happened? Let's just review what happened. While performing a safety check, reactor 4 technician allowed the power surge to reach, get this, 120 times the rated capacity of the reactor. Anybody want to guess what this technician was doing? Taking a break, couldn't have been watching a video. No, what? No, didn't have cell phone. But anyway, you get it. So this is neglect. 120 times, right? You say, well, where were you when it went 30 times, right? The bells. And what that also means is someone had disconnected the bells. Perhaps occasionally the bells would ding, ding, ding at 10 or 15. So what happens when you get tired of hearing that bell every day you go to work, right? It always goes that. Every day it does that 110. So you shut it off. I don't know, okay? These are all speculation. You get the point. This is neglect, okay? So basically it ripped the core apart. That's what happened. 4,000 tons of concrete blown away. That's a lot of concrete. And it blown away because this is like dropping a nuclear bomb 100 times Hiroshima. That's what they did. Okay? So, half-life of 24,000 years. Okay? Shot them a mile away, mile and a half away. And here's what happened. What did we get? These beta. We got the Incredible Hulk radiation. Okay? This is why it was such a problem. We got this level of radiation. And from that, a lot of people died. Physical death and then years and years after. Really horrible. So how is radioactive radiation measured? It's measured in what's called RADS, or radiation absorbed dose. Absorption of 0.01 joule of radiation per kg of tissue. So your weight matters when it comes to this. Okay? All right, so 0.01 joule of radiation energy per kg. So there you have it. Okay? And then you have a REM. Okay? It's QX number of rads, where Q is the relative biological effectiveness factor. So that's really a factor that's thrown in there. But the real bottom line, 1 SV equals 100 REM. So what I expect you to know is that radiation is measured in rad and REM. Okay, we expect you to at least know that much about radioactivity. Occasionally when scientists work on certain projects, you have to wear a radioactive monitor to see how it's working. I worked on a project once and I had to wear one. That's what I did every day. I go into that lab, I put on my monitor, I come out, you had to turn your monitor in and report it. And so that's just how, I'm not glowing, am I? But anyway, you have to do that, okay? So that's what they do, they measure it, and if it's dangerous, you get this color, you get this, you get the color. But anyway, So you wear these monitors, and people that work in nuclear, it's kind of normal. That's what they wear. So here's what you want to know. Watch this. No observable effect. You're okay here. White blood count decreases slightly. White blood count decrease. You've heard of that when you do cancer treatment, right? Okay. So you essentially, huge drop in white blood count, nausea, vomiting, loss of hair. These sound familiar? Okay. So it's like getting cancer treatment here. And I want to make sure that I'm real clear on this. Hopefully I'm not sounding to be disrespectful of cancer victims. This is horrible to have to go through this, okay? But this is what happens. And now you get ulcers and then death. I typically ask you about some of the signs of radioactive poisoning. And so I'll ask you, and these will be on there. Yes, sir.
At what point does the radiation poisoning become untreatable?
I don't know that exact answer. I'm not going to go on a limb on that. I could talk about it, but I don't recall the exact numbers, so I don't want to misquote that. Okay. Yeah.
But there are points on the
There are.
where
Where it's time, Yep. You can't turn it around fast enough. Okay. Yep. At some point, yep. And I don't recall what that is. I'll check that though. That's a very good question you just asked. I'll check what the stats say. Okay. I'll give you that. Okay. Very good question though. I'll probably have to add that to the next class. I'll look that up. Okay. We'll add it to it. Good question. But now, I should remind you also that I am not a medical doctor. There's my disclaimer. I am a scientist. Okay. So, over 1,000 injuries, firefighters' death, 150,000 people had to evacuate Ukraine. I have some friends who have relatives from the area. You talk to them about it. It's just really, if you get to hear it, right? It's a different thing. You read it. Okay, you read it. You see it on CNN News. All right, you read the videos. But when you have friends who had relatives that went through these experiences, it is really kind of gripping to hear about it. Estimates future cancer, and this is what you ask. Millions. Okay. Radioactive particles in the environment and the food chain. Yeah, this gets back to your question. So it becomes all part of all of us. Large amounts of uncertainty and fear of the population? Absolutely. Because of this, harnessing this energy. So some policies were put in place and some things happened. But one bottom line is people started mistrusting the government. Okay? And so this is a concern when people talk about putting up nuclear power plants. And because they start to think about, remember what happened? They say, well, it's not going to happen again. Well, yeah, there are no guarantees about that. So there are lots of political concerns, and we will go into these details. But then you see what happened to Fukushima. This was caused by a natural tsunami, okay, a flood, okay, which resulted in meltdown of 3 reactors, okay. So the water knocked out the electrical generators needed for the cooling water. So what happened? You have this superheat, right, coming at you, superheated steam, okay? Overheating the fuels, then started a chemical reaction, generated hydrogen gas, okay? Hydrogen gas was vented to release iodine-131, which we just saw iodine-131 on the previous slide. Is one of those species that came out, Chernobyl, you get it? Not good is the point here. You can read all the rest of the details, but not much more. Despite venting, explosive reaction occurred at 4 of the 6 reactors which released radioactive isotopes. So you get the point here about nuclear reaction. It has a lot of energy. Little material, okay, a lot of energy. That's what makes it such a good option for fuel and for energy, but it also is dangerous. Therefore, I'm going to say, why not use something that's natural? Solar power. The sun rays hit Earth every hour with enough energy to meet the world's energy demands for the entire year. You say, then why don't we use it? Well, that's because only 1% of electric power is generated in the U.S. comes directly from solar energy. It's not a choice. It's been implemented real well. Some parts of the planet receive too low of intensity for the light to be useful for it. The U.S. Southwest states receive the highest amount. So why don't we just put it out where it's a lot of energy and pipe it in? Well, then you got to run pipes. But here's the other problem. Solar panels. Being able to put enough solar panels to generate the energy requires using land. Well, no one wants to put those solar panels on their land. And you get it? So you have these trade-offs again happening. Okay? And you have to say, well, gee, I'm pretty cool using the fossil fuels. I'll keep just burning my wood stove. I don't even use the city's gas. I just burn my own wood. So why don't everybody just chop their own wood? You get it? Or whatever the case is. Whatever the argument is. But the point here is, to date, there have not been enough solar panels erected to take advantage of the natural sun. That's the real bottom line. You talk, well, why don't we put them on top of the buildings? We got all kinds of arguments about that and against it. And again, people giving up the land to solar panels that they really don't want to do that, because the same people who want to use the natural sun want the natural earth, oftentimes. You get it? So you have these arguments for and against it. It is an option, but it's an option that is not being well executed around the world. That is the take-home message. But let's talk about how this science works. This slide is on the exam. Silicon, the heart of the photovoltaic cell. There you have it. Okay? I typically ask a question like, what material is needed to produce photovoltaic cells? And someone will say sunlight. The answer is silicon. That's the answer. Okay? Light of certain energies can free an electron between silicon atoms in the solid. So you have this, it hits it, and it frees it, and it creates a hole, essentially, so that we can get, so that basically electricity can work. The electron then moves through the crystal lattice, making silicon an electric conductor. So it moves through, making silicon an electric conductor. In order to increase the efficiency of silicon, is doped with atoms containing either electrons N-type or P-type. Typically that's boron or phosphorus type of materials, and they dope it, and that helps increase the transport of energy through the silicon atom. And without going into the rest of the gory details, which actually I could, we won't, essentially missing electrons are a hole created here. So electron can move into the hole. And because it can move into the hole, voila, we get silicon acting as a photovoltaic cell. So it's the movement of electrons within the silicon lattice through holes created by doping the silicon with N and P types of materials. Oftentimes that's boron and phosphorus. You will need to know that. You will need to know that these photovoltaic cells need doping with minor impurities to be efficient. Okay? So silicon used in photovoltaic cells is doped with minor impurities, which helps create the holes to make it more efficient. And so here we get, we create what's called P-junctions. Solar cells contain layers of P-types and N-types, silicon placed in direct contact, and we basically build these layers. And you see here, we have the P-type hole, E-type electron, and this basically is sandwiched together. And because of this construction, because we have these holes and electrons, can flow, and you can use your cell phone light, okay, at the concerts. That's why you get to do it, okay? So solar cells contain layers of P and N-type silicon placed in direct contact. So we get this, we can get this electricity. When light hits the N-type silicon, electrons are freed from the crystal structure and they move the external current, eventually returning to the P-type side. So it must complete its cycle. Electricity always has to do that, by the way. The electrons have to complete their cycle. When electrons are released by the sunlight, holes will also generate in the P-type. These electron holes pairs move in the opposite direction, and you still generate electric current. That's how solar energy works and operates. So the fission of solar cell, only photons with enough energy can knock electrons free from the doped. The doped is the impurities that are added to increase the efficiency, silicon lattice. As of 2015, silicon-based solar cells have efficiency of only 21%. Now you get, does everyone follow? So you're putting up all these, but you're only still getting 21%. The technology just is not there to do what its potential, what it potentially could. Multi-layer cells increase efficiency about 50%, but are very expensive to produce. These designs feature many layers with thicknesses on the order of tens of the microns. So you can increase layers to get up to 50%. But that's still as best we can get out of the technology. So does anyone get the picture when it comes to generating energy? It's challenging. Okay? And there are pros and cons of the fossil fuels and the nuclear fission process and the solar cells. So what about other renewable sources? What about the windmills out on your way to Lansing if you live here, right? Go through Breckenridge and over there, right? Okay. Among the possible alternative sources of energy, wind power, and you will want to know this, has been the largest growth over the last decade. So if you follow the scale, wind's been growing, and this is hydroelectric. Hydroelectric has consistently generated the most electricity since 1990. Hydroelectric, water electric, you get it? All right? However, the average generation of hydroelectric is 300 billion kilowatts, which is much less than the combustion of fossil fuels, which is 3 trillion. Does everyone follow? So what the bottom line is, fossil fuels still rule because you can get the most energy out of these. Okay? That's why we keep burning fossil fuels. The top 5 countries of geothermic, so that means basically geysers, okay, Old Faithful, generate capacities are shown here. You can read them for yourself. But you have the U.S. all the way down to New Zealand when it comes to geothermal. But it's still not enough to power Saginaw Valley State University, all of the universities in the state of Michigan around the world, to put lights up in the football stadium, to have lights for March Madness and things of that nature. Just not enough from these renewable sources. So we tend to rely still on fossil fuels. You guys have survived our topic of energy, fossil fuels, and electricity, and alike. Enjoy the rest of your day.